All right, so now we're to a point where we get to determine the pH of aqueous weak acid solutions. And this is really cool because what we do is we use an ice table, and we've had limited exposure to ice tables, but we'll increase that exposure now. And we identify the initial concentration of a weak acid. We use the change, and we use the equilibrium concentration, and we place the equilibrium concentrations into the mass action expression, right? And then we solve for the Ka, which is the concentration of the quotient, or the quotient for all the different concentrations at equilibrium. And then from that, we use the resulting hydrogen ion concentration, take the negative log of it to get the pH. Did that make sense?
I had you for a few seconds there, but no, I didn't quite get that.
All right. You can go back and listen to it again, but it's really not that necessary to understand right off the bat. We're going to do some practice problems and we'll learn how to do it. Okay? One thing we want to remember is that we can drop that term. And do you remember dropping the term?
Oh, kind of. I don't remember how we can know.
We'll firm up that understanding as well. So, we're going to determine the pH of a 0.1 molar solution of acetic acid. Okay? Let's go back a bit and remind ourselves, what's the pH of a 0.1 molar solution of HCl?
Oh, not that, this one, different one?
Yeah, what's the pH, question mark, the pH of a 0.1 molar solution of HCl?
How do we know?
Well, remember, HCl is a strong acid. So this is essentially saying, what's the pH of 0.1 molar H plus ion?
Oh, then you just take the negative log.
That's right. And the negative log of 0.1 will be 14. Negative log of 0.1. Oh, sorry, 1. Right. Negative log of 1 is 1. So the pH would be 1 because the 0.1 molar hydrogen ion comes from the 0.1 molar HCl. But that's not the case for this acid because this acid is a weak acid, right?
Yeah, acetic acid is a weak acid.
So to answer this question, we need the Ka. We need the Ka. And what we need to do is we need to picture, I'm going to move this up out of the way as we kind of work on this ice table. So we need to picture the HC2H3O2 dissociating into the hydrogen ion and the acetate ion. Okay? So we create our ice table here using 0.1 molar as the initial concentration of the acetic acid. How much of these do we start with?
It doesn't say. How do we know?
Well, if it doesn't say, then we have to assume there's none, right? I mean, that means there is none. Now the change. What is the change for this process here? Well, if we put this in and there's nothing here, that means this is going to have to dissociate into those two over there because there's nothing here, right? It can't go back this way. So there is going to be a shift to the product side. So we're going to lose some of this and we're going to gain some of these products over here. All right, and the equilibrium then is 0.1 minus x. The equilibrium here is 0 plus x, which is just x, and 0 plus x, which is just x. Now, can you help me write the equilibrium expression for that equation?
Yeah, so products, which are H plus times C2H3O2 over the HC2H3O2, the acetic acid.
Very good. Concentration of acetic acid. That's my equilibrium expression for that reaction. And I can see that this is going to equal, at equilibrium, a value of 1.8 times 10 to the minus 5. These are what represent the equilibrium concentrations in terms of the variables and the values that we know. So I can just plug those in. 1.8 times 10 to the minus 5 is going to equal x squared over 0.1 minus x. But I can drop that x because this 1.8 times 10 to the minus 5 is much, much smaller than my 0.1. And so I can solve for x simply by taking 1.8 times 10 to the minus 5 times 0.1. And then we're going to take the square root of that answer. So it's 0.0013. X equals 0.0013. Now what do I do with that?
Is that the shift?
That's right, it is the shift. Can I do something with that shift?
Well, you need to find the pH, right?
I do need to find the pH.
Well, X also equals the hydrogen ion concentration at equilibrium.
That's right. The hydrogen ion concentration at equilibrium is X. So this is the hydrogen concentration at equilibrium. So if I want to find the pH, all I have to do is what?
Take the negative log of 0.0013.
That's right. Negative log of 0.0013, and that pH is 2.87. Okay. So again, we created the ice table. We had the concentration of this reactant. Initial concentrations of these products were 0. We looked at the change. We're going to lose some of this as it dissociates into that. We're going to gain a stoichiometric equivalent amount of these. And then the resulting equilibrium concentration is 0.1 minus X, which we're going to drop that X term because of this value being so small compared to the 0.1. And then we have X and X over here. We take the X squared divided by 0.1, set that equal to our equilibrium constant. Now, why did we put X squared over 1?
That's a good question. I don't know.
Well, remember, the Ka, the K for this reaction, right? 1.8 times 10 to the minus 5. It equals the equilibrium expression, which is the concentration of products over the reactants. And the concentration of products at equilibrium were X and X, and the concentration of the reactants at equilibrium we decided was going to be 0.1.
Oh, yeah, okay. So that's where that came from.
Very good. Okay. How about this? The pH of 0.1 molar HCN with, now, can you identify the pH of 0.1 molar HCN without the Ka?
No.
If I asked you previously, what's the concentration of 0.1 molar or what's the pH of 0.1 molar HCl, and we could do it without a Ka. Why is that?
Oh, because that's a strong acid, but HCN is not a strong acid.
Okay, very good. So we have to create ourselves an ice table again. And we also have to have the pKa. Now, if they don't give you the Ka, or the Ka, if they don't give you the Ka, you'll have to go look it up in the table. But what are we going to do here?
We're going to create an ice table. We're going to write HCN dissociated into H plus and Cn minus.
Very good. And then what?
Then we're going to look at the change. The change is going to be, it's 0.1 mole. So no Cn minus or H plus N, right?
That's right.
So it's going to be the same as this one, minus X plus X and plus X. And then the result is going to be X squared over 0.1 again equals 6.2 times 10 to the minus 10.
Can you see that fast?
Well, I think so.
Maybe we should let the folks try to do that at home, copying this material and find out what the pH of the resulting solution is.
Okay.
All right, so we created an ice table, 0.1 molar, none of this stuff. The shift has to be negative, right?
How did we know it was negative?
Well, there's no product over here. So if there's no product, there's no way that a shift is going to change to the other direction. If you wanted to calculate the Q value and compare it to the K value, you'd find that the Q value was essentially 0 because the products over that value is going to be 0, right? So that's another way to think about it. But yes, the products are going to have a plus X, and the reactants are going to have to lose an X.
Okay, and then the equilibrium is 0.1 minus X, but we drop that point, or that X, and then x squared on the other side.
Very good. And then x squared over 0.1 equals the Ka. Again, this x squared is coming from our equilibrium expression of H3O plus its concentration times Cn minus its concentration over the concentration of HCN, right, at equilibrium. That equals 6.2 times 10 to the minus 10. The hydrogen ion concentration we decided was X. The cyanide ion concentration at equilibrium we decided is going to be represented by X. The HCN concentration at equilibrium we simplified to 0.1. So that's where we get this x squared over 0.1 equaling 6.2 times 10 to the minus 10. And solving for x, taking the negative log, that will give us our pH. Okay, excellent. Now let's do the same thing, but this time let's look at the pH of a base that is placed into solution. So determine the pH for 0.1 molar solution of, and now again, before we move forward, I want to see if you can identify the pH of a solution of 0.1 molar NaOH. What's the pH of that solution?
Do I have the Kb or I don't know. Do I need the Kb?
We don't need the Kb, do we? We don't need the Kb because this is a strong base. Therefore, the concentration of 0.1 molar HCl, or sodium hydroxide, is just the negative log of 0.1, because 0.1 molar sodium hydroxide, strong base, that means 0.1 molar hydroxide ion results. Negative log of that is 1. Is that the pH of our solution?
I guess so.
No, because this is the hydroxide ion concentration.
Oh yeah, so 14 minus that.
That's right. So 14 minus 1, that's going to be a pH of 13. Okay, that's a good place to stop.